So what I want to talk about today is development of an automated solution for drone-assisted assessment of field trials. Yeah, to give you an introduction, UAVs or drones can be used for different applications in agriculture. We can use them for so-called prescription maps to make farming more efficient. We can detect plant damages. We also do fawn detection before mowing, weed detection, plant protection, and other things. What I'm going to talk about specifically today is breeding and finding out how we can improve breeding. So why do we do a field trial? So what does a field trial look like? If you look at these images and in the center of the slide, you can see what a field trial looks like. On the on the top side, you can see a fertilization trial, but we also do plant breeding in order to find out which breeds fit much better for different climatic conditions, and especially which breeds are resistant to drought stress, looking at climate change. Yeah, what is the state of the art? The state of the art you can see on the photo in the center. People are walking around on the field and they're looking at different plants. This is called visual plant scoring. It's very subjective. It needs very good training, and it's extremely time-consuming and cost-intensive. And the alternative is to use drones, because we've got continuously better and less expensive sensors, including cameras and other things, that can fly over large areas, and it avoids plant damage. So we've got different traits, which you can see on the right-hand side, which we are looking at. And our main trait in this project was to find out whether we can predict grain yield and whether we can say something about drought resistance. Okay, so our project goals were to build a pipeline for automated processing of drone data, and to evaluate different prediction models and spectral sensors in different growth stages. So materials and methods were 2 field trials, which you can see on the left-hand side, both in Germany, and we were using 2 different sensors, a normal RGB camera and a multispectral camera from a company called Tetracam. Yeah, this is this is how our workflow looks like. We've got the spectral data, which are basically photos taken by the drone. We extract them for every single parcel, and then we're comparing it with the scoring data, which we are getting from the field, and we are using different AI or ML models in order to predict the output. Yeah, results. If we look at plant height, how high are plants? That's a pretty important trait, and we saw that we can very well visualize or very well establish a method for measuring plant height from drone images rather than walking around in the field. And as you can see on the right-hand side, saying how high a plant is a very difficult thing. So with these results, we've been very satisfied, and we're pretty sure that we can predict plant height from drone images. Lodging is something you can see on the left-hand side. Lodging basically means that if we're overfeeding plants with nitrogen, that they're falling over. On the right-hand side, you can see the results, the scoring results from people who were walking out in the field and scoring, and the results from the drone images. And we can see that we were able to match very well with machine learning the degree of lodging compared to the visual scoring. So lodging can be automatically detected on a very large number of parcels. I'm talking about a couple of thousand parcels automatically with drones. Plant density, we've developed some algorithms based on convolutional neuronal networks in order to count plants, and even to count single ears, which you can see on the right-hand side. So that worked pretty well. I want to dive a little bit deeper into yield prediction. Well, yield is basically a pretty good measure for drought stress, and you can see on the right-hand side, based on a specific example. So we use this specific spectral index called the NDVI. We used the random forest model, and we used the drone data from the 8th of June 2020 in order to predict yield. And you can see here that we had an R squared of 0.68, which is pretty good. Yeah, at the same time, what we saw was that an important thing to find out the right moment in time to take the images. So in some moments of time, this is a day of the year on the x-axis and the R squared on the y-axis, we can see that with some sensors, RGB sensors and some indices, at certain dates, we got the highest R squares, especially over here. You can see that we even came up to R squares of 0.8 if we use the right sensor and the right spectral index in order to predict yield. Yeah, that was the year 2020, and if we look at the year 2021, which was different with respect to weather, we can see that the patterns are completely different. What you can see on the y-axis is that the R squareds in 2021 were much, much lower. So we were not able to properly predict yield in 2021, although we used the same models and we took photos at the same growth stage. Yeah, here we look what happens if we take basically pictures of all from all 10 different dates in 2021 and in 2020. And we saw that even here between the years, we have got a large difference. In 2021, we got an R squared of in the range of 0.3, whereas in 2020, we were in a range of 0.7. And here you can see that different date increments or different dates contribute differently to the ability to predict yield. Yeah, and this is for me the most fascinating slide. We compared different machine learning models. This is only a selection of different machine learning models which we used. And if we look at the maximum R squared, we can see that in all cases, support vector modeling was basically the best method we could use compared to the other methods. But we can also see that we had a substantial difference between the year 2020 and the year 2021. So basically a baseline is if you've got good data, it doesn't really matter which machine learning method you're using, you're getting good results. But if you've got bad data, as in 2021, then it doesn't help to select the right machine learning model. Yeah, we also looked at the modeling effort with respect to training time, and we saw that some methods, especially random forest, is pretty intense when it comes to calculation power, which you need, and it basically increases with the number of predictors which we were using. Yeah, we also looked at the pixel size. Initially, we started with a pixel size of 10 centimeters or even lower, and we increased the pixel size, and we saw that the pixel size did not affect the results at all. And a last thing we tried to look at is, we talked about diseases in the talk earlier. We tried to detect plant diseases. In this special case, it's leaf septoria. And we saw that the results were not very satisfying. So until now, we were not able to detect plant diseases from drone images. Yes, to give you a summary, we see a large potential in using drones and machine learning for supporting plant breeding. Plant breeding has got a lot of issues because we want to use less herbicides and pesticides. We want to use less fertilizer and to produce more grain and other products in order to support feeding the world, especially with a background of climate change. Yeah, as I've shown you, some traits we can determine very well, and with other traits we still have difficulties. And basically machine learning helps a lot, but not in any cases. So I'm looking forward to the discussion later on and to any questions you have, and thanks for your attention.